Well, before we talk about heat production, we need to understand how heat is measured. It's measuring using a calorimeter. Various kinds of calorimeters have been used successfully to measure heat by the cold fusion process. And we'll go through the 4 of them just to show you how they work. The single-wall isoparabolic calorimeter was the one that was used by Pons and Fleischmann initially, and it's the most simple of the 4. It consists of measuring the temperature within the electrolyte, within the electrolytic cell, and measuring the temperature outside of the cell to get the temperature drop across the cell wall, which is proportional to the heat flow. The outside temperature is easy to measure because the cell is usually in a constant temperature bath. The problem comes in measuring the temperature inside the cell. Because heat is being generated within this liquid by electrolytic action and hopefully by a cold fusion reaction, convection currents are formed, and these cause temperature gradients to occur. Therefore, it's difficult to know precisely what the average temperature in this liquid is. Pons and Fleischmann got around this problem by clever design. Other people have stirred this liquid to eliminate or at least reduce the temperature gradients. Nevertheless, this is a problem that can be solved by using a second wall or a double wall isoparabolic calorimeter. Here, a wall outside of the electrolytic cell is used to measure the heat flow by measuring the temperature on the inside of that wall and again on the outside of the wall. The temperature difference across the wall then is a measure of heat flow through this material. And you'll notice that the temperatures are now independent of what's occurring within the cell itself. A Seebeck calorimeter is similar to an isoparabolic calorimeter in the sense that this wall contains hundreds and sometimes thousands of thermocouples that are wired in such a way as to produce a voltage that is proportional to the temperature difference. So instead of measuring an actual temperature across the wall, a voltage is generated that is proportional to the temperature difference, and it is proportional to the temperature difference of the average temperature throughout the wall structure itself. As a result, it's more accurate than simply measuring the temperature at a few places. The flow type calorimeter is somewhat different. It causes liquid to flow past the outside of or through pipes on the inside of the cell, carrying the heat out by warming the liquid that is flowing through this cooling channel. The cooling channel water is frequently used, and the temperature of the water entering the channel and leaving the channel is measured. Well, the methods for calculating the heat from these various techniques is fairly simple. In the isoparabolic techniques, the temperature difference is multiplied by a constant, which is the calibration constant that needs to be determined by experiment. And it's determined, I might add, by either placing a resistor in the cell through which a current flows, and the amount of power that is being generated within that resistor is then used to calibrate, or a dead cathode, one that does not produce any excess energy, is used, and the calibration is done by applying electrolytic current. In any case, one multiplies the temperature difference across the barrier times the calibration constant, which can be more complex than just a simple number, I might add. From this is subtracted the amount of power going into the cell, which is the product of the voltage times the current. That difference is the excess power. In the Seebeck calorimeter, instead of a delta T, one uses the voltage that is proportional to delta T, multiply that times a constant, and then subtract the power that's going into the cell. The flow calorimeter calculates the power somewhat differently. The temperature change of the liquid is multiplied by the flow rate and by the heat capacity of the liquid. if all of the heat went into the liquid, then this would be an absolute type calorimeter that would not require calibration. However, very few are absolute, and so a small correction factor is found to be necessary. This type calorimeter typically has an uncertainty of about 50 milliwatts. The Seebeck is somewhat better. It has an uncertainty of perhaps 20 milliwatts. The isoparabolic calorimeter is, depending on whether it's single wall or double wall, the single wall, 100 milliwatts perhaps, if you're fairly careful. The double wall can be much better than this. There are two kinds of calorimeters, the open type and the closed. In the open type calorimeter, the gases that are produced by the electrolytic action are allowed to leave the calorimeter. This takes energy away from the calorimeter, and this energy must be calculated properly and applied to the equations to calculate the excess properly. On the other hand, many modern calorimeters use the closed method. That method uses a recombiner in the gas space above the electrolytic above the electrolyte, and this catalyst combines the deuterium and oxygen back into water that goes back into the cell. As a result, nothing leaves the cell, and so these corrections don't have to be made. Well, let's look at the many studies that have been reported about energy production. This is a histogram comparing the number of occasions when the amount of power along this axis was reported. And I might point out, this is the report from each individual study that gave the highest amount of power. Many studies got more than one sample to turn on, and this compares only the most energetic of the samples in the set that they report. Well, first of all, you can see that occasionally very large amounts of power have been reported. This is 200 watts, so this is about 180 watts. Here's 100 watts. This is an extraordinary amount of power, much in excess of what the error in the calorimeter would be. But as one goes to lower and lower power, it's seen more and more often. If we take this region here and amplify it, magnify it, we can see the detail now. Again, there are significant amounts of power being reported, down to a couple of watts. But most of the studies produce power even less than that. So you can immediately see that not only are large amounts of power produced, but a significant number of studies have been made that produce an amount of power that's well in excess of the error in the calorimeter being used.